Hey everyone, today we are going to talk about intramolecular forces. So let's get to it. Intramolecular forces are forces that hold atoms in a compound or molecule together. So if we looked at our example here, ammonia, NH3, we would be looking at these bonds right here. In contrast to intermolecular forces, we would be looking at the forces that hold between different molecules together. So we'd be looking over here. We'd be looking at that bond over there. Sorry for the sloppiness. So for intramolecular forces, there's two big basically, different kinds. We can have like ionic or covalent forces. Ionic forces, ionic bonds, are when there is electron transfer. So if you didn't know, the E with the negative sign is short term for electron. It is the transfer. That's very important. The transfer of electrons between two atoms. These are typically strong and have a large difference in electronegativity. So let's write that out too. Electronegativity. And we have our periodic table here. A good rule of thumb when you're looking at the periodic table, you could get increasing electronegativity this way. Highest electronegativity is fluorine right there at 4.0. And then when you're looking this way at the periodic table, it is decreasing. For the covalent bonds, you have the sharing of electron pairs. There's a small electronegativity difference, and then even within covalent bonds, the bond strength and the melting point and boiling point are lower than you would see in ionic bonds. And within the covalent bonds, there's 4 different types that we'll talk about right here. We'll start with the nonpolar covalent. There's a very similar electronegativity, and it would be equal electron sharing. So a good example here is really any of these elements that are the same or very, very similar on the electronegativity scale. So we have, 2 chlorines bonded together. They obviously have the same electronegativity, so they would be considered nonpolar covalent, just because of how close they are on the electronegativity scale. Now let's move on to the polar covalent, and that would be, those are atoms. Oops, let me get in the right color here, not to mess everything up. Atoms with electronegativity difference of 0.5 to 1.7. So let's look at that. Let's look at a little example here. Let's scroll down. We will look at HCl. Okay, so HCl, and the electronegativity difference is between 0.5 and 1.7. And the more of an electronegative atom will be attracted more strongly, and the one that's more electronegative, will gain a partial negative charge. So let's look right here. And the more electronegative atom is obviously chlorine, so we would give that a partial negative charge. Let's do that in a different color to make it clear. Let's do it in black. And there, and then the more positive side, hydrogen, would get a partial positive charge. And then you can also get into dipole movements, and that is denoted like so. And it has a plus on the more positive end, see that plus right there, and then it is pointing to the more electronegative atom. And that is basically it points to the pull of electrons. So the electrons are pulled this way more. So that's why we get that partial negative charge right there. Let's move on to coordinate covalent bonds. So that happens when shared electrons are derived from a lone pair on only one of the bonded atoms. So you're probably like, what does that mean? Well, let's look at an example. That's the best way to learn. So let's say these two compounds, these two molecules were trying to bond together. So we see that there is a lone pair right here, right? This is the lone pair of electrons. And that is a coordinate covalent bond. We'll see right here when they come together. So that would be the coordinate covalent bond then, just because we have that lone pair right there. And that's the only lone pair. So boron doesn't have a lone pair on it, but we see it on the nitrogen over here. So that is why it's a coordinate covalent bond. Let's move on to the last type of covalent bond. We're going to look at metallic bonding. That's just basically when metal atoms are joined together. So metals joined. And at this point, we have the electrons that become delocalized. And that is what you hear about the so-called sea of electrons that you've probably heard your chemistry teacher refer to. And that just means that the electrons are free to move throughout the solid. And this allows for the conduction of heat and electricity. So those are two very solid, solid traits. So the last two things that I want to talk about here are just two characteristics of intramolecular, covalent bonds, really. So we have bond length, and that is exactly what it sounds like. It is just the length of the bond. So if we have single bonds, let's do... If we have a single bond, so say we have HCl, that would be the longest bond. And then we have, that would be the shortest, just because of how many bonds there are. And then we, see, we have a double bond, that would be in between. And that's just bond length, strictly bond length, nothing else. when you have single bonds, the longest all the way down to the shortest when you have a triple bond. And then we have bond energy. And that is just the energy required to break a bond. And the higher the bond energy, that means it's stronger. That would mean it is harder to break. So that's all for today, guys. Thank you very much for tuning in.